In this lesson, we're going to investigate a number of different circular areas. In order to investigate the various kinds of circular areas, we should begin with the area of a whole circle first. In order to estimate the area of a circle, we're going to want to convert it into an area that we already know how to find. To do this, we're going to unroll the circle in the following way. We'll start by marking the center of the circle and an axis that comes out of it, which we'll call the d-axis. We've drawn this so that this point over here represents d equals 0, and this point over here represents d equals r, where r is the radius of the circle. This length over here is also equal to the radius of the circle, where this is 0 and this is r. Let's pretend that I selected some random distance, which I'll call x. Now we can go ahead and trace out the circular arc where d is equal to x. And now we can go ahead and unroll it into a straight line. Now as you can see, this is just the circumference of some circle, and we know that the circumference of any circle is just 2 pi times r, but in this case the radius is just x. Now if we look carefully at this, if we were to half the radius x, then we would also just half the circumference in turn. Now as you can see by this picture, these circumferences take up some of the area of the whole circle. So if we were to just cover the circle with lots of these, then we could find the area of the whole circle. Now just like we did with the example before, we can go ahead and unroll all of these along the length axis. Now whilst this is a crude approximation of the actual area, we can see that the area is approximately equal to the area of this triangle over here. Now we know that the length over here is just equal to the outer edge of the circle, so it's just equal to the circumference 2 pi r. Now from this, we can say that in order to find the area of any circle, you can just convert it into the area of a corresponding triangle. Now from this, we know that the area of a triangle is just half its base times its height, so therefore we can say that the area of a triangle is just 2 pi r times a half. And this means that the area of any circle is just pi r squared. Now, for full disclosure, if this is actually going to be true, we're going to need way more than just 7 of these bands over here. If we truly have lots and lots and lots of them like this, then eventually we will reach the limit where a equals pi r squared. Now there are actually some other circular areas that I'd like to introduce you to, so I'm going to go ahead and do this on a new page. Now to begin with, I'm going to bring back the circle and the unwrapped version as well. Now the next thing I'm going to introduce to you is called a sector. You can think of it almost like a slice of a pie. We can also visualize the space taken up by the sector with this picture and this picture as well. Instead of finding the area of this big triangle over here, instead we're now finding the area of this smaller triangle over here. If you look at each of the strands over here, you'll notice that each one also shrunk by the exact same factor. Therefore, this means that the area of this new triangle is just a fraction of the area of this old triangle over here. In order to find a general formula for this, I'm going to start with a specific case first. So suppose we started off with some metal disc, and we wanted to paint a sector of it with another color. Now we want to estimate the cost of painting this part blue. The particular blue paint that we want to use costs $2 per square centimeter. Now in order to approximate this cost, we're going to need to start by finding the angle. Say in this case we found that the angle was approximately equal to 100 degrees. Now since there are 360 degrees in a full circle, then the fraction we're after is just 100 over 360. 100 over 360 is just the same thing as 5/18. Now the total area of this whole circle is just given by pi r squared. And we know that the radius is just 10 centimeters. And this just ends up being 100 pi centimeters squared. But we only want the area of this blue part over here. And we know this blue part is just 5/18 of the total area. Now we can go ahead and use a calculator to figure out what this is equal to. Now we can just go ahead and double this to get the cost, which is approximately $174.50. And all this really shows us is that this paint is way too expensive. Now we can go ahead and repeat these steps in general to find a really convenient formula for this. We're going to want to start by finding this fraction f. And to do that, we're going to have to know what this angle over here is. So let's go ahead and label it theta. Now, assuming we've measured theta in radians, then the fraction we're looking for is just theta on 2 pi. Again, we've chosen radians because it makes the final formula very pleasant. Now, as we said earlier, the area of our sector is just given by f pi r squared. So therefore we can write, and after crossing off the pi's, we get that the area of the sector is just theta on 2 r squared. Now we're going to look at one last circular area, which we're going to call a segment. So as you can see, a segment is the same thing as a sector, but we've just cut away this little triangular area over here. Again, we should show you how to find the area of one of these segments with a practical example. So let's bring back the other example we used for the sector. Suppose that we decided that the blue paint was way too expensive before, so we decided to paint a smaller area instead. Now we can say that the area of this segment is just equal to the area of the sector minus the area of the triangle. Let's go ahead and call this one A1 and call this one over here A2. And the area we want to find is called A. Now this 5/118 over here is just the number of revolutions and an angle of 100 degrees. So the first thing we need to do is to find our angle in radians. That's actually pretty easy because we could just swap revs for 2 pi radians. And now this just ends up being 5 pi on 9 radians. Now first off, we know that the area of our sector is just half r squared theta. We know that r is 10 and theta is 5 pi on 9. If you put in all the numbers except pi, you'll find that you just get 250 divided by 9. Now to find the area of this triangle over here, we should just go ahead and draw it. Now we know that the area of any triangle like this is just half times the product of its two sides times the sine of theta. And now 10 squared divided by 2 is just the same thing as 50. And now we can write down our area A as A1 minus A2. Now we can go ahead and substitute this into a calculator, but you should be careful because since we have this sine 5 pi on 9, we have to do it in radians. Now we notice that 38 times 2 is just $76. So now that we know how to do this, we should go ahead and repeat these steps on the general case. So the area of the segment is equal to the area of the sector minus the triangle. If we label the area of the segment AG, then we can just immediately say that AG is just half theta r squared minus half r squared sine theta. Now in this equation, we can see that half r squared is just a common factor, so we can remove it. And now this gives us our final formula over here. AG is just half of r squared theta minus sine theta. And now we've finished our discussion on the circular areas. We know that if we want to find the area of a whole circle, we just use pi r squared. If we wanted the area of a sector, we just use this half r squared theta. And if we want the area of a segment, we just use this half r squared theta minus sine theta. And this completes our discussion on the circular areas.